Hello, everyone. Thanks first to Michael and everyone here for the invitation. It's really nice to come and meet a lot of friends and hopefully make new friends. My name is Luis Pacheco. Everyone calls me Luigi. Everyone can call me Luigi. I don't know the reason. It's just the way everyone has called me for many years. I'm an assistant professor at Florida Atlantic University, where I have a lab called the Interactive Machines Lab. I'll talk to you a little bit about my trajectory. In 2012, I founded a 3D printer company in Mexico called MakerMex. We started making open source 3D printers, but then we started making our own in 2014. In 2018, I went to Barcelona to get my master's at IAC with Aldo. He's somewhere around here. And then when I went back to Mexico, I got very curious about using robotic for 3D printing. I started developing some custom cells for 3D printing using KUKA PRC mainly. And then in 2021, I moved to the US, where I founded a company, NeoBrutal, for digital design and fabrication, integration, consulting mainly. And then I got the opportunity to join FIU as a researcher there to do my doctorate degree. And then in 2025, I got another opportunity to actually join as assistant professor in FAU, similar in Miami area. And in 2026, I finished my doctorate a couple months ago in what I'm going to present. So hardware is hard, and robotics are probably a lot harder. I'm assuming everyone has worked with them. You know that if you integrate something in a KUKA, it's not going to work directly in an ABB. If you bring a UR robot, then same problem, right? So there's a lot of things that make it hard for anyone to start working with robots. Now, when I was an FIU, I was tasked. The kids were coming, and they were like, oh, how can we make something fun for them? So I made an interface that allowed them to make drawings really quickly. All the kids were like loading the picture and being able to draw in like 2 minutes. And I figured out that robotics doesn't have to be hard. I just think that the interfaces that we have made around them really suck. And I divide this problem in 3 things. One is spatial understanding. Everything in robotics is relative, right? You have the relative coordinate to the base, to the tool, to the blah, blah, blah. And this is a hard abstraction for most people, including me. The hardware integration, as I said, is complicated. Every robot has a different language and a whole different way to talk to it. And interaction complexity. When we want to do something else than a serialized list of commands, it starts becoming really hard. So, and this has biased us, right? When we think about a toolpath and we just see a list of targets, this has led us to think about, to constrain us in how we think about the problem and how we solve the problems with these machines. Now, before I go into the rest, I want to speak a little bit about why Blender, why open source. Well, mainly like when you make your stack in closed source software, first you have licensing fees, things like that. If they update it, they might break it for you, and then it's a problem to update it. If they discontinue the platform, you're kind of screwed. And because it's closed source, you don't have a way to fix it. Now, if you keep an open source stack, then you control the full stack. There's no licensing fee. You can patch and fork any layer of your process, and you can reproduce these across any machine. Now, going back into the research, I wonder how can real-time interactive environments reduce these spatial and cognitive challenges that non-specialists have? In his talk in 2012, Brett Victor, he presented this demo where this is a kind of a UI for programming video games, but as you change the code on the video game, the programmer can see in real time how this is going to affect the gameplay. And I think this is really, really interesting. So how does that reflect in robotics? Well, first of all, if you already have a robot, why not have a digital twin at all times when you're designing? And that gives you the spatial relativity to the physical world. In this case, 3 different robots. You move the robot, you see it update in real time in Blender. I'm going to jump that. And then this is the idea of interactive toolpath. This one takes a minute to load. But the idea is you have a target, right? You move it on 3D space the way that you will do anything. And then why not just tell the robot, OK, go there, move. and then the robot just moves, right? So it's this kind of dialogue with the robot that makes it easier to understand how is it positioned relative to anything around it. This is my toolpath, do it, and then the robot goes and do it, right? Oh, it was too close to the table, let's move it up a little bit, trial and error, and making it easier. By the way, this is in my garage. I got a robot there. And this is interesting because then you can also use the robot as a means, as an instrument to measure the world around it. In this case, one of my students measured the rock and then printed some toolpaths on top of it. And then going to the next problem, how can modular and decoupled hardware simplify the end-effector integration? And most importantly, enable reconfigurable workshops. I'm in a lab, in an academic lab, so having that flexibility is very important. Here's, for example, the case of an extruder. And in this case, you think about the extruder not as something that you integrate to the robot, but something that's parallel to it. So as you're talking to the robot, you're talking to the extruder. And there's like, with ESP32, it's so easy now to make these network devices that allow you to do that. So how does it work? For example, if you still want to use the digital I/O of your robot, you can stream this to MQTT, and then the extruder will instantly react to those digital I/Os, but at the same time, you can stream them directly to Blender and directly avoiding any extruder integration to the robot. This is interesting because in Blender, you have attributes. So you have the points, your targets, but then you can have 1,000 attributes per point. So this is really interesting because each point has metadata, and you can use this metadata to make smarter toolpaths. And then again, stream this to the different end effectors that are related to that spatial point. You can see here a little bit on the list how it looks: linear speed, fan speed, extruder speed, if the extruder should be enabled. And something interesting that this allows is that in real time, this is a graph software prototype that I made, but for extruder. But if you are getting, for example, a knob, when you start printing, you usually use a knob to change the speed. At some point, you can replace that knob data and change it with an OpenCV algorithm that is measuring the extrusion rate. So if it's under extruding, it will overcompensate on that. And it's just reconnecting live, and how do you call it? Like hot. So that's really interesting because it gives you this flexibility as things are happening. And in this case, it's the same firmware running a massive dimension pellet extruder and a WASP clay extruder. Same firmware, different extruders. It also works with different robots. Now you're not constrained about the robot. And these are some examples of what I have, right? You have smart knobs. You can have the I/O from the robot streamed. You can have the extruder, LEDs, external axes like motors. Other industrial extruders, like in this case, a Caracol extruder. And then in the interaction complexity, how can procedural and behavioral abstractions enable accessible robot control? We have learned a lot about. We have taken a lot from animation and game industry. I don't know if you are familiar with Mimic for Maya. So you keyframe the robot, and then you kind of go through the timeline, and then you simulate the robot. So you think about time and pose, and then it interpolates that. But then most interesting, there's this concept of procedural animation where you don't animate everything manually, but like you tell each leg that it should not go through the surface, for example, and then you animate it in that way, and each leg knows what to do and how to behave. And this is a really interesting concept for robotics. NVIDIA is actually using that concept in some of their deployments, recent deployments. In this case, this robot, I think they control it with a handheld device. And then you think about the higher level actions, walk, and then the trajectory is now not important because you teach it how to figure out the trajectory, right? How does that look a little bit into a robotic arm? In this case, you have the toolpath. It's a little bit dark, but as you move the toolpath in real time, the robot reacts in real time, right? So as the robot is running, the toolpath is getting updated by the user, and you have this direct way of changing things. I'm going to skip that one. And then again, this is how it might look in a KUKA robot. It just takes like a minute to load. And now the target, instead of commanding it to go, literally, it just goes to that in real time. You just, and then you can animate that with animation constraints. And in this case, instead of programming the trajectory for each robot, I just tell each robot to look at each other. And as I move one robot, the other one knows how to do, and one knows how to look. So there's no trajectory, there's just constraints. And then they kiss. Something interesting is, for example, with VR now, it's really easy to align the robot now. You draw a toolpath in there, and then you just tell it, okay, now go and do that toolpath. You can see how the overlay is working. And this is actually a hack, because I use the boundary to kind of make it transparent and then record it. But it works. But you can see the toolpath, and then the robot, and then give you that. Same thing, you can deploy this in a handheld device, and then control it with your Steam Deck. Very useful, like for the site, I guess. This is what we were using with the kids. And again, like Animaquina currently supports mainly KUKA, Universal, and U-Factory robots. More coming soon, hopefully. You have a toolpath visualization with all the benefits of the of Blender, right? Like nicer materials, lighting, and multiple ways of looking at things. You can simulate thicknesses, all these different things. You can again use it to simulate, for example, as I move the robot up, like what's the layer like. You can also see the errors in the print. Change the layer height on real time, and then it's super reactive, right? Millions of points, and you get a reaction in half a second. And again, everything stays procedural and in real time. So in this case, we have a simple base. We can enable the toolpath, the slicer, and then simulate it, change the layer height, modify the geometry. This is too long. I need to make it faster. So at some point, I go into it and modify the geometry in real time, and then you see it changing instantly, right? You don't need to wait for anything. You can see the seam, you can see where it starts, where it ends. There you go. And again, you are drawing the toolpath in real time there. Same thing, non-planar. We have a lot of these is actually, Alessandro Somparelli has an add-on for G-code generation, and then I've been using a lot of that and translating it into robotic toolpaths for geodesic, topology slicing, regular, directional slicing, for any type of slicing. Because of geometry nodes, it becomes really easy to make very complex toolpaths. Like in this case, this is kind of one planter, but then you can just say, okay, let's arrange more, and then it automatically calculates all for you. And again, everything stays reactive and able to simulate how it's going to look. You print all the bases for them first, and then you print the objects on top of this. Conformal 3D printing, in this case, the rock, we measure it with the robot itself, and then we print on top of it. And in the other case, we have a mold, and then just by identifying 2 points in Blender with the robot, then we know exactly where that thing is, and we can print on top of it with a lot of precision. These are student projects. And this is interesting, because how does this idea of procedural animation applies on fabrication? Milad, one of the students at the lab, he's moving in real time the tiny mill thing. And then we put a constraint, a sign distance field from the surface that is like a magnet that prevents him or tries to push out of the surface. So it's really interesting because now there's no toolpath. This is kind of hybrid between sculpting and CAM. You get the precision of CAM, but you're sculpting. So it's interesting because you're getting best of both worlds. And again, this works with multi-robots on the same scene. Actually, as you can see in this example, I don't know if you notice, but there are actually 2 robots. One is holding the stock. So you can come in the VR environment, rotate the stock, and then grab again your milling and do it again, and keep doing that. And again, as many robots as you want that can be doing things in synchronicity. Yeah. It's been deployed. One of the early adopters is Massive Makes that has been using it. In this case, we added just a direct control of the motors on the extruder, and then you can analyze this in real time as the robot is working. You can see exactly where it is. If something goes wrong, you can recover from that specific point and not waste a print. And I think that's one of the largest non-planar prints that we have made of that column with Animaquina. So I took a picture when I came and visit. And again, you always see the robot in real time. Some workshops, Fab24, PA Academy, in Acadia 2024, in Ecuador, in University de las Americas. This one is interesting because the students in 1 week develop custom end-effectors and toolpaths and a whole strategy. So here you can see one is doing light painting with the robot and using Blender physics simulation for this. So using a different tool actually opens the scope to what you can do and how you think about it. Drawing with sand. I don't know if you can tell what it is. You just need to look at it. It's inverted in purpose. Again, 3D printing with clay with the students. This was a month ago with Joan invited us to do a workshop in Taiwan. And these are very interesting projects. In this case, you can see some students mapped the mic on the laptop, and then the robot is just making a circle, but then from the input from the mic, it changes that toolpath in real time. So now people were yelling at the laptop, and then the robot was changing the drawing in real time. Some projects, Joyce Villet, 2023, we made all these planters for her benches with custom texturing and that. So it's the same algorithm, just different texture, and it produced one piece 1,000 times, and it's different every time. Dancing columns with Joseph Choma on 2024. We made like 12 columns like this. And then this year, Edouard Duval-Carry in my garage, I built this column for him. It's currently at the Venice Biennale. This has been published in a couple places. Again, it's used that I know in 5 academic labs at least. An industrial partner that I know is using it, using teaching robotics and art and design projects. And then before I stop, before I end, I want to show you a video. Sure. And it's the same thing that you see, is just a little faster. This is a project for my friend Madeline Gannon. All right, thank you.